In our first example, we are going to be solving this first order linear differential equation. I know this is first order because the highest derivative of y that shows up is the first derivative. So now we're going to check, is this differential equation in standard form? And it's in standard form if it comes in this form here. Form is that the coefficient to the derivative dy dx should be 1. Then whatever is in front of y we will call p of x, and the expression that is on the other side of the equation we will call q of x. So our differential equation is in standard form because our coefficient to y prime is 1. If I rewrite the equation, it would look like, place the y prime with dy dx, just so it matches that form. There is a 1 in front of this dy dx that we do not see, plus y. There's also a 1 in front of this y that we do not see. And on the other side of the equation, there is an e to the x. So matching this form with what we see here, we can see that our p of x is 1 and that our q of x is e to the x. Now that we have identified p of x and q of x, we can go on to identify our integrating factor. Abbreviate integrating factor as IF, and the integrating factor is equal to e raised to the integral of p of x dx. That is what the integrating factor is when solving a linear differential equation. In our case, our p of x is 1, so we have e to the integral of this p of x here is 1 dx. The integral of 1 dx is simply x, so our integrating factor is e to the x. So what we're going to do now is we are going to take our integrating factor of e to the x, and we are going to multiply that through by everything in our differential equation. So our differential equation was initially dy dx. I'm leaving space in front of this intentionally. Plus y, I'm again leaving space there, is equal to e to the x. I'm going into all three of those terms and I'm multiplying all of them by our integrating factor. And the reason that we do that is that after we multiply the left side of the equation by the integrating factor, this side should always turn into the derivative of the integrating factor, which is e to the x, multiplied by the dependent variable y. The whole reason that we use an integrating factor is because it transforms the left side of the equation. If you're working with a first order linear differential equation that was in standard form, so it fit the form that we started off with where we had 1 in front of dy dx. Let's look at what we have underlined in red. I'm saying it's the derivative of the integrating factor times the dependent variable y. Well, to take this derivative, we would use product rule. This would be f times g. F prime would be e to the x, and g prime, the derivative of y, would be dy dx. But what we have here is exactly f prime multiplied by g. There's f prime multiplied by g, which is y, added to g prime, which is dy dx, multiplied by f. So that left side is exactly product rule on this product of the integrating factor times the dependent variable y. And that will always happen when you're solving a first order linear differential equation using an integrating factor. Now that is helpful for us because remember our goal is to solve for y. At this point y is on the inside of this derivative operator, and so to get rid of the derivative operator we're going to take both sides of this equation and we are going to integrate both sides of this equation with respect to x. On the left side, the integral and the derivative operator cancel each other out, and we're simply left with e to the x multiplied by y. On the right side of the equation, in order to integrate the product e to the x times e to the x, I'm going to use u substitution, where u is e to the x, So du is e to the x dx. So our integral is simply the integral of u du, which we know is u squared divided by 2 plus c. In this case, our u was e to the x, so this will be e to the x squared, which is e to the 2x, divided by 2 plus c. I'll go ahead and plug that into the other side of our equation. Integrating the right side gives us e to the 2x divided by 2 plus c. Our goal is to solve for y, so now I'm going to come in and divide both sides of this equation by e to the x. I'm dividing all three terms of this equation by e to the x to be left with y is equal to, I have a 1/2 from that 2 in the denominator, and then when I take e to the 2x and divide it by e to the x, we're simply left with e to the x, and then here we have ce to the negative x. And this is our general solution for this differential equation. Here we have another first order, because the highest derivative of y that shows up is the first derivative, linear, because x and y are, y is only showing up with an exponent of 1, differential equation that we want to solve. We're going to solve that using an integrating factor, but before we can introduce an integrating factor, we have to make sure that our differential equation is in standard form. That means that we want the coefficient to the derivative to be 1, so that we will be able to see what p of x is in front of y and what q of x is on the other side of the equation. So I do see my dy dx and my y already set up how I would want them in the equation, but the problem is that the coefficient to dy dx is currently not 1, it is x. So I've just replaced y prime with dy dx. I'm going to go into this equation and make the coefficient to dy dx 1. So we're going to come in and divide all three terms of this equation by x, leaving us with the new equation dy dx minus 2 over x multiplied by y is equal to x. So now I can see that my p of x is negative 2 over x and that my q of x is x. It is important that you take the sign of p of x with you. You take that minus sign with you there. Now that we have identified what p of x is, we can go on to find our integrating factor, which is generally speaking e to the integral of p of x dx. So our integrating factor is going to be e to the integral of negative 2 divided by x dx. The integral of negative 2 divided by x dx is negative 2 natural log absolute value of x, and I don't have to use the absolute value because we do have the condition that x is greater than 0. Rules of exponents tell me that I can send the coefficient of negative 2 back to the exponent on x. This is from, I said rules of exponents, but I meant properties of logarithms tell us that. So that this is e to the natural log of x to the negative 2. And then the e and the natural log cancel, and we're simply left with x to the negative 2 as our integrating factor. I will rewrite this as 1 over x squared. So now that we know what our integrating factor is, we're going to take our integrating factor and we're going to multiply the entire equation through by it. Remember, this here was our equation in standard form. So I'm going to take the standard form of the equation and I'm going to multiply each term by the integrating factor. So the first term of dy dx is multiplied by the integrating factor. The second term of negative 2 divided by x multiplied by y is multiplied by the integrating factor. And the term on the right side of the equation of x is also multiplied by the integrating factor. The reason that we do that is because the left side of the equation then completely collapses into the derivative of the integrating factor, which is 1 over x squared, multiplied by the dependent variable y. The right side of the equation I will simplify to simply give me 1 over x. Now we're trying to solve for y, so we're going to integrate both sides of this equation with respect to x. When we integrate the left side with respect to x, the integral and the derivative operator cancel out and leave us with y divided by x squared is equal to, when we integrate the right side of the equation, we get natural log absolute value of x. I'm only going to put x because we did have the condition that x was greater than 0. Don't forget your constant of integration. The last thing I'm going to do is I'm going to solve for y, and I'm going to do that by multiplying both sides of this equation by x squared to get my general solution for this differential equation.